Yeah, welcome from my side. So I give the, let's say, a little bit extended welcome talk. What is this place where you are, what we do here? So I want to show you a little bit why we build accelerators very shortly, a little bit, a few examples. What is an accelerator actually, and why exactly look they exactly like this? Yeah, we have this claim you probably saw on the on your invitation. We explore the universe in the lab. So what does it mean? I mean, what we in principle want to do is we want to answer questions like what are the smallest building blocks of matter and how and why and where and when were they created, and for that we have to somehow get the matter or the state of matter, which is in something like this was happened here at the beginning. This is the Crab Nebula, and in the middle was a supernova explosion. This is all kinds of different material and gas thrown out. You can see it with a telescope, and then we want to have the matter under this temperature, energies, pressure in our lab. Yeah? Or how does a neutron star work? How does it look in the inside? How does this nuclear matter forming the neutron star behave? This is a very, very high pressure, high magnetic field and things like that. And for this, to get matter into this, what let's say from from our viewpoint here on Earth, very extreme conditions, you need a particle accelerator. And this can, for example, look like that. Yeah, you can have two heavy ion nuclei. So this is a nucleus of, in this case, it's gold on gold. Actually, if you're sitting on one of them, they are round, that they are flat like this. You only do to the relativistic speed if you look from the outside. And if you see they hit each other, a lot of different new material is created. And if you want to look into this very hot collision zone at the beginning, there you have matter like in the neutron star. But then you only have a very, very short time to look into, and it's very tiny, and you have a lot of background. So you have a lot of data coming at you, and you want to find the few particles which actually have been there. Yeah, most of the particles just can tell you, I know somebody who has been there. Yeah, and only a very few particles have been there where they were so hot and so dense, and you try to find them. So it's a lot of data you have to process. This maybe gives you already an idea. So, but how do you do that? So first of all, from the accelerator from the experimentalist point of view, they are very often would be happy with an atom. But from the accelerator physicist point of view, which I am, we need an ion at the beginning. So an ion was an atom before. You can add some electrons or remove some electrons. In our case, we always remove electrons. So you have a positively charged nucleus, and you have electrons around. If you remove a few, the gross charge of the thing becomes positive. So it's electrically charged, and as soon as you have something electrically charged, you can influence it with electric and magnetic fields, and that's basically my job. We start here, this is how it looks. It's a big place. You have, here is the ion source, there's a small, and for example, the one I show here works more or less like the principle, like the neon lights from the ancient times before the LED lights, yeah, where you had a gas discharge in this nice color. And the basic principle of acceleration is super easy. You just have your positively charged ions, which is not easy to do. We have a complete group working on that. And you take a very high voltage. You take two metal plates. As soon as the positive charges see positive charge, they're repelled and they're attracted to the negative charge, so you can accelerate the particles. And this was actually done, yeah, one of the very first accelerators built, and even some used today use these DC acceleration thing. This is of course boring for the GNU radio kind of thing because it's not accelerating alternating voltage. But it has another problem. It has its limits. So the highest power supply you can normally buy gives you a few 100,000 volts, maybe 1,000,000 volts. And if you transfer it to a lab, your maximum accelerating voltage you can get is 10, 20 million volts. That's it. After that, you have discharges all the time, it's not work. The world rocket is something like 30 or so, but our users, the ones which want to explore how this neutron star works they need billions of volts for accelerating the ions, and this you cannot get by this means. And now I have to make a confession. This is a confession of all accelerator physicists, basically. We cheat the ions all the time. We take a very low alternating voltage and make them believe that they're accelerated by a lot on a very high voltage, but we always use the same low accelerating voltage. And this is for example, in the case of our first accelerator here, it's RF with 36 or 108 megahertz. So we are all getting in the RF regime. How is it done? Let's just assume we have here a bunch of, I have a photo soon, a bunch of so-called drift tubes. These are metal tubes with a hole in the middle. And we put this voltage on them. And if you do it right, the ion comes out of one of the tubes. It sees the accelerating part of the voltage and gets a little faster. Then the voltage goes to the opposite sign, and normally it would decelerate the particle again. So if you put the particle in something like that with a AC voltage, will just oscillate it forth and back. You will accelerate it a little, but then break it down again. But here, then it is, if you do it right, in this moment, it's in the next tube. And the tube is a piece of metal around the ion. Maybe some of you have heard of a Faraday cage. So this ion doesn't see the external field. So what it does, it just drifts with a constant speed forth. And then, if my colleagues from the linear department did everything right, if it comes out of this hole, there's again the same voltage accelerating it a bit further and further and further. And by this means, if you make this drift tubes longer and longer because it gets faster and faster, you can accelerate in principle to very, very high energies, and even could do this experiment with the neutron star. If you have about 1 or 2 major power plants and a lot of taxpayers' money, because this linear accelerator would be kilometers long and use gigawatts of energy. So this is something you can do for, we call it low or medium energies, but in the case of our accelerator, which is right over there in the next building, so we are here and it's over there, 130 meter long, so it's just the other opposite building, you can get to something like 20% speed of the light. Yeah, and then we go to circular accelerators, but first a picture inside. It's actually very funny because Sharp is on it. It was done by public relations. It's just the official picture of the Unilac, but I like it very much, so I put it in. So this is part of this linear accelerator, and more importantly, that's how it looks in the inside. Beware, if it's operating, you don't want to be standing there, first of all, due to the X-rays, and moreover, because it's completely vacuum emptied of air, because you can, of course, not try to accelerate your ions if it's all full of air. It's a little bit like you want to do a dash world record in a crowded space. It doesn't work. You need free space to run. So that's why we evacuate them. But here in there, in this little thing, there's an ion beam, and there you have the drift tubes, and actually this complete thing is an RF system. So it's the first stage. Huh? This has stages. Is this a pre-stage and then 4 stages? And the funny thing, it's a nice question. Actually, we can operate them. We can leave something away, so we get different energies. So you can accelerate to a certain point, and the rest is switched off, and then the particle drifts. And that's why our users, even behind the linear accelerator, can get the particles with different energies, which is quite important to them. They don't want to not only want fast and many particles, but they want them at a distinct energy, which is not available on all accelerator labs. Yeah. And here we do something like the same trick. So we take the beam from so you need the linear accelerator even for the ring accelerator, because we inject the beam, and we have here a structure made out of these red things, we call them bending magnets. In principle, it's a big magnet, north and south pole, and if you shoot then a charged particle in, it's deflected perpendicular. You maybe remember that from grad school or from high school. Yeah, there was a rule with the fingers and so on. So most of the structure is meant to bring the particles back to the same point. The yellow ones are magnetical lenses because as in any optical system, the particles tend to drift apart and you have to bring them back. Otherwise, they will hit your vacuum vessel and be lost. It's something we want to avoid. It's actually something why we need exactly to know what the beam is doing, and GNU Radio comes already in the game. But first of all, we want to bring them back to the same place. Why? Because we have an acceleration cavity, we now call that. It's one place we can put RF on the particles. And then again, it's the same trick. If they are here, they see the accelerating part of the voltage. And if they are on the other side, it would be the decelerating part of the voltage. And by this means, we can make them faster and faster, round by round. This comes, of course, with new problems because these ions, they get faster and faster. Therefore, the magnets have to get stronger and stronger. It's like if you drive your bicycle or your car. If you go faster around the corner, you need more force to keep you on track. So this is why we have to ramp up the magnets. And now comes a real nightmare from the RF point of view. At this, from the high energy physics point of view, still low to medium energy, they actually change their velocity. So the frequency they arrive at the accelerating cavity gets higher and higher too. So we go to our RF engineers and tell them, yeah, we need a high power RF system, but we want it to change frequency in a very controlled manner and fast. And if you know, many of you are RF engineers, what you want is a stable system which never changes frequency. So they are very mad at us, but we give them a lot of beer and so on, and so they still build it for us, and that's why we can accelerate the particles. So and that's where the name comes from, because you have to be synchronous with your RF frequency and your magnetic field, otherwise you get no acceleration. And then if you have accelerated enough, either to the limit of your magnets or to exactly the energy the user wants, you can extract the particles towards the experiments and smash them on something and create matter in this very extreme states like we have in the universe. That's how it looks from the inside. You have here this bending magnets, you have here the magnetic lens. This is already in higher order. It's something like you have a cylinder at your... Please. We can,
sorry for the
for the outsiders, yeah. Well, I can repeat it. The question was, do we have to accelerate them applied or do we have a signal? You have actually several signals. You can have put a transformer at some place of the accelerator, and there you can measure the particles going through. It gives you a current. What is much more interesting for us is actually we have kind of plates along the accelerator, and there we sample with very high frequency the electric signal which is created by the particles inducing space charge into these plates. And if you sample this with a very, very high bandwidth and very fast, and you do a Fourier transform of it, it actually gives you the revolution frequency of the beam. It tells you the energy spread, so how good you hit your energy or if you have strays. And it even can tell you something how often they oscillate per round around their, from us, wanted orbit. So there's a lot of information in that. And this is something which Shahab is total expert in. Getting the signal, he even got the PhD for the, something like that. And, and he can tell you in the order of 10 to minus 6 to 10 to minus 7 the revolution frequency of these guys in the ring. And from that, for example, even later in an experiment, if you put them in a storage ring, you can get the masses of the heavy ions, or the fragments of heavy ions, which is then very interesting information for the physicist, because with a very often quoted, I would say, most famous equation in physics, E equals mc square, it's a binding energy. So you can make very exotic matter, put them in a ring, measure the signal, and it tells you what the mass is in the binding energy. So there's a lot of signal processing involved. Otherwise, we go blame. So thank you for the question. Perfect question. Yeah. So what we do with it, 2 examples, very fast examples. I will not go into detail. We developed a cancer therapy with heavy ions here. That's what maybe some people read in newspapers about. So we treated over 400 patients here at GSI with carbon for tumors, mainly in the head areas. It was so successful that a dedicated accelerator was built by us at the Heidelberg facility. And back to basic science, this is basically our mission. We are a basic science lab. We created quite a few of new elements in the periodic table of elements. So it's what you know maybe from your chemistry class in school. And here are some with a distinct color. I think they even come up. It's the element 107 to 112. They were actually firstly created here at GSI with our linear accelerator, and they even got named by the science group. It's 107 Borium, 108 Hassium for the federal state of Hessen we are in, 109 Meitnerium for Lise Meitner, very famous German physicist, Darmstadtium for the city of Darmstadt, Röntgenium for Konrad Röntgen, he invented the X-rays or found the X-rays, and Copernicium for Copernicus. So you'll find them in any chemistry book on this planet. So Darmstadt somehow left the mark there. And this is the nucleotic charts, or the periodic table of elements for the physicist. In one direction is protons, in the other direction is neutrons. And these black ones here are the ones which you can find in nature. And all the other ones are the ones our scientists want to explore and do science with. And quite a lot of them, the orange ones, were actually discovered here at GSI. Moreover, most of them can be produced here. And as nature usually is, nature is never fair. The ones which are most interesting are the ones which are hardest to produce and live only a very short time. And that's basically why we built the new facility, because we want to go further out here in all directions to go to we call them exotic matter, which is more interesting for the users. So how we do that? We have we want to extend our worldwide already worldwide unique accelerator to new capabilities, and this will look like that. Yeah, this is the present facility. This is our construction site. Most of the civil construction is done. We are in the south part putting in right now the building infrastructure. In the north part, it's building infrastructure and already parts of the accelerator you will see tomorrow. And what we want to reach is, a factor of 100 to 1,000 more intensity of the primary beam. And for secondary particles, the ones which we make out of the primary beam by smashing it on some wall or some target, we call it, even a factor 10,000, but a 10 more. Moreover, we can go a little higher in energy. That's interesting for some physicists too. So the question is how we do that. I mean, it's not that the present facility is not running at full speed, so we have to have ideas how to improve that. So, of course, you can upgrade the existing facilities. It's done continuously. We have actually at GSI, our uniqueness is that we are a heavy ion lab. So you can, as a experimentalist, you can basically order any ion from protons to uranium. So the stable ones you can have from the source in the accelerator accelerated on your target. You can even have different energies from shot to shot, and even different ion species from shot to shot. So you can have a user who gets a nickel and the next one gets a gold, shot to shot. And then even if you created fragments, you can store them in storage ring and keep them for some time and investigate them as long as they live. It makes complete sense, because if it's hard to produce a particle, it's good to save it as long as possible and investigate it. But what does more intensity bring you? Come a little bit how the science here works. It's publicly funded science. So if you have a good idea and want to do an experiment, you can go to our Experimentausschuss. There's smart people, actually our scientific concurrence guys from all other labs of the world, once per year, and you propose what you are what you want to do. And then they have to judge, is it feasible, is it not feasible, is it best done at GSI or somewhere else, and is it, of course, interesting enough to be granted beam time, we call that. So you get that. And this is all a yes. There might be even one more problem. It might be that what you propose is super interesting, but it uses a lot of beam time. Yeah, to get the right signal, the right amount of statistics, we maybe would need the complete accelerator for half a year. And then they would say, sorry, no, we have so many users, we cannot do that. But if I can increase the primary intensity by a factor of 100 to 1,000, you can do it in 2 days or on a Saturday morning. And then suddenly things become feasible, which were not feasible before. So it's not just a mere factor or something. It opens up gates to new physics, which you could not explore before. That's why it's interesting to increase the intensity, about factor 1,000. How you do that? One of the things is, of course, improvement. Then we made already the existing synchrotron faster. It's 10 times faster now. It's already a factor of 10. So it could give you one beam. Wait for the microphone for outside users, yeah.
All right, yeah, thank you. Just out of curiosity, because you mentioned 90% light speed with the current facility, will this change with a new planned one?
This will go a little bit faster. It goes for protons then to 99% or even, so. But at a certain point, they don't get faster, they just get heavier.
Okay, that makes sense.
As a CERN is still at 99.999% of speed of light, but so in the speed difference, it's not a big difference, but in energy, it's a lot. So what amount of energy you put in this? Why we usually, unless it's an outreach talk or for non-experts, we always talk only about the energy of the particle, because it's what there's a capability of reactions it can do, what particles it can produce if it hits something. But at least here, the speed still gets considerably faster, and even with this one a little faster. But my point is why you do that. So as we started this business and upgrading, we could deliver beam once in 3 seconds to our users. With all the upgrades, the present machine, the synchrotron, can deliver beam 3 times per second. So it's roughly a factor of 10 faster. Actually, it's not usable in this speed by the present users, which are all here, but it's good as an injector for that one. So it's the first factor of 10. And then we leave a stripper. It's just one example. So why I could explain all the rings and why they are produced like this. It takes over 1 hour. I did that as a German outreach talk. But I want to give you one example what gives you an improvement, why you do that, and why you need a new accelerator then. And it's that we leave a stripper away. Well, it sounds a little bit sleazy. What does it mean? So if you accelerate your charged particles, they come out of the ion source with a certain charge. For example, in case of our design particle, the uranium, it's 4+ from the charge. It doesn't mean that all the from the source. It doesn't mean that all the uranium created in the source have the electric charge 4+. There are 2+, 3+, 5+, more of them. But you take the most abundant one, and the others are already lost. And here's exactly the point. Whenever you choose a charge, you lose all the other charges. So then we accelerate a little bit in the linear accelerator, and then we actually hit our beam on a gas jet in ultra-high vacuum. That by itself is a technical marvel. So you let gas fall into the ultra-high vacuum, you hit it with ions, you pump it away, and the ions still think they are vacuum, but this short place, and then they are due just kinetic interaction, they lose more electrons. And it again gives a charge distribution, leaving us with uranium 28+ as the most abundant one. That's already a very strange system. You have uranium 28 electrons gone, so the usual chemistry lab cannot do that anymore. And then we accelerate them further, and shortly before we inject them into the synchrotron, we hit a thin foil, and again we strip off charges, and the most abundant charge state is 73+. So you get a distribution like that. So it's not like you change and you get all the same outfit. No, you change and you get very, very many different outfits. So if you stay with soccer, you have Barcelona, Bavaria, Madrid, Rome, and so on. And you only can accelerate one of the teams. You know how it is with fans and one buff. So we have to choose one. And by this, we throw 6/7 away of the beam. By just leaving the stripper away, we gain another factor of 7. So with the increased speed of our present machine, and this measure already gained a factor of 70, but I end up with a highly charged beam. It's higher intensity, okay, and it gets even a little bit more stable. It's a little advantage for the experts, has less space charge, but it's not. But you cannot accelerate it as easily. So the maximum energy you can get out of our present machine is too low for the experiments. That's why you need a new accelerator. So we don't build the new accelerator just for fun. In principle, we need it to get this high intensity beam to more or less the same energy as before for the same experiments, which bring you from, we need half a year to a Saturday morning. And for this, we built the SIS 100. It's over there on the construction site. The tunnel is built. It's actually double tunnel, one for the accelerator, one for all the devices, power supplies, and so on for the different devices in the machine. And you get an additional benefit. You can even go higher in energy. You can even accelerate protons as far that you can produce protons and antiproton pairs. So even new physics opens up, which was not possible at all with the old machinery. So you have the same thing we're doing right now, much better, but you have new things in addition too. Basically, as a trade-off of the machine, you have to build anyway to fulfill the first capability. So this is one of the designs. Of course, you see a lot of storage rings. Here's a storage ring. There's a storage ring. We will see one live tomorrow. Sharp is one of the world experts in the storage ring business. So if you are there with him in the ESR, I'll ask him lots of questions. He knows everything about it. And especially he knows what signals the storage ring can deliver and what you can do with it. And there comes GNU Radio in. So my message to you is, yeah, you're here at guest at the world leading science center. We build accelerators a little bit for fun too. Yeah, I like to operate them. I try to improve them. But of course, we get questions and requirements for the beam by our experimentalists, which uses facility. They come from all over the world. And this is basically gives us interesting tasks and challenges which we have to meet. And for that, we have to process lots of data. And you saw we putting RF into our machines. And if you look at a single spot of an accelerator, you have bunched beam, we call that. So it's not a continuous beam. These are always packets of beam passing by. And this is actually, if you look just at the plain physics, it's RF. So we put in RF and we get different RF out. On there, we have very many places GNU Radio can come into the game. And thanks to Ralph and his team and Sharp and the experiment, we was more a little bit on the experimentalist side. We use it at very many places already. Yeah, all our we modernized all our RF systems. A lot of software-defined radio went in, and old analog devices were thrown out. And of course, we process the data coming out that the physicist at the end can write nice papers about cosmic matter, which has not been investigated before. So at this point, I want to thank you for your attention, and feel free to follow us online on several places and give your comments, post your photos, ask questions. Of course, ask questions to me right now. Thank you.
There's a few mentions of 0.7 Hertz, 2.7 Hertz. In general, what are the frequencies? So you mentioned 140 something megahertz, but what is the stability and what is the kind of frequency that you're handling?
So there we have different frequencies involved. Actually, the linear accelerator runs in a 50 Hertz mode, so it makes one bunch of particles with every periodic time of our power grid network. So it's synchronized with the power grid network. To accelerate it, we use 36 megahertz and 108 megahertz in the linear accelerator. And in the ring accelerator, we use frequency from 500 kilohertz to 5 megahertz with two different systems. So it's not the same system. One has half the frequency of the others.
And these are frequency that you feedback as a function of your ion acceleration capability, or are these high stability local oscillators?
Actually, in the LINAC, it's a high stability system. Even the LINAC itself, this tank I showed to you with a drift tubes in, it's part of the accelerated system itself. It's the oscillator actually.
It's an oscillator. Mm-hmm.
Yeah. On the synchrotron, because you have to change the frequency, it's basically a transformer driven with an RF power supply. Yeah. So and of course there are means done to get it somewhat in resonance. So we change. There's a big stack of ferrite in, and you can change the pre-magnetization of it over the cycle. But in principle, even our RF guys say it's a fast transformer. Yeah. But of course, the source is a completely valid RF source with a software-defined radio before thing, and there it's all not directly on feedback. Actually, I didn't talk about that, but we are of course working on feedback systems. We have even experts here which stabilize the beam. You can even in the storage ring, there are different means of cooling. I will talk about that tomorrow if we're there. But one of the means of cooling is actually look at the displacement of the beam, take this signal, invert it, put it back on the beam to somehow push it back on the other side. It's called stochastic cooling. It's such a clever idea that it even gave a Nobel Prize to an accelerator physicist to Mr. van der Meer in 1984, 85. Yeah, so there are lots of more of RF signals which are used or feedbacks. Yeah, but the main accelerating voltage is more or less steered. You give a ramp in amplitude and frequency, and we run that over the cycle. But some accelerators use actually feedback on that. They measure the magnetic field and follow with the RF.
Maybe I can comment on that, on the challenge, especially for the CIS-18. I mean, when the particles are very slow, you need a very low revolution frequency. But when you extract them, you need up to 10 megahertz. Now, those of you who have built a phase-locked loop, be it digital or analog, you all know they like not to be moved. So maybe you can change them by 1% over a second. These PLLs, or these frequency drivers, these DDSs, have to change frequency from, for example, 200 kilohertz to 10 megahertz within 100 milliseconds. And if you have a too high phase instability or noise, you start shaking the beam, and protons or ions, they're a bit like elephants. Treat them bad and they will never forget you. So they're basically, the size of the bunch will become bigger and bigger and bigger, and you can't easily cool them. So we have to handle all the beam parameters with highest, most care to keep the beam small and very precise in their transfers, but also longitudinal dimensions. Also, I like your PG explanation of stripper. I was a bit worried because if my wife is watching at home. There's also like a non-PG version of explaining it. One of the issues why we want to minimize the stripping is it's basically like if you have people who take off clothes, sometimes get ugly and people take more and more distance. So the problem is the more you strip those particles, the more space they occupy and the more they repel each other because they don't like each other. So to keep everything PG, we say like, no, let's strip as little electrons as possible because this allows us to put more particles in the same spot in the accelerator. And that's one of the ways how we accelerate to very high intensities. But to keep this only partially stripped ions in the machine is a delicate things, and you can ask some of my colleagues on that side. That's the reason why we have ultra-high vacuum systems to make sure that they not lose any electrons while being accelerated. Any more questions?
How do you generate your frequency? Do you have atomic clocks or GPS stabilized?
Yes,
or just
we have atomic clocks, and the synchronization of the accelerators actually is GPS stabilized. So because you have not only the clock for your RF, but you have to sync different clocks over the campus if you want to shoot from one accelerator to the next. And this is GPS synchronized. Its name is White Rabbit protocol. Okay. So you can give timestamps to your things and start the accelerators at the right moment. Because if I am ready with beam from the one synchrotron and Shahab is waiting at the storage ring with the storage ring for beam, the bunch length is 300 nanoseconds. You have to be quite exact in time that it finally reaches the next ring. This is synchronized with GPS.
But you have a centralized frequency that you distribute.
Yeah, exactly. Yeah. Okay. So it's two. Yeah, the individual machine has its own clock, but then there's this centralized White Rabbit system which synchronizes the machines.
White Rabbit, for those people who haven't heard this is like a P2P standard on steroids. So you synchronize this down to below nanoseconds, picosecond level.
Yeah, thanks for the interesting talk. What's happening on the detection side? So at the collision, what sensors do you have there, and is GNU Radio used there? What are the key parameters?
It's actually a hard question for me. I can explain in principle what sensors they have. We even will see one tomorrow. We will walk in. You have actually a stack of different sensors. One are so-called multi-wire chambers. There's a gas-filled chambers with some wires in, where you can then in the gas, your particle going through makes a little bit of ionization. The wires suck out the charge, and then you look on both ends of the wire for the signal, very tiny signals. You have to amplify them. You have very many wires, and then you can reconstruct the path. Other things are just at the end of the path. CCDs, like you have in the camera of your phone. But actually it was the other way around. They were invented for particle physics and then went to the camera. And you have a lot of scintillators, so you have special materials. Most of them are plastics with some exotics in, cesium or so. And then if a particle goes through, it makes light, and then you put light amplifiers on both sides, do the same trick from the difference of the signals. You say where it passed, you know your geometry. But at the end, what you have is big data. Yeah, you have 10,000, 200,000 channels, and right now in the experiments, like we have them here or at CERN, for example, they still trigger. So they have some signature on when does something interesting happen, and then they write away all the data. And it's already that amount of data that you don't see that much online. They have some signatures, but it has to be processed offline. So you have 4 weeks of bean time and 2 years of data evaluation. In the future, which is completely crazy, we have a group here for the detector which will go here, CBM. They want to leave the trigger away because they always say, oh, you never know what might become interesting in the future. You want to have all the data. If there's new physics found, we can look into our old data and see if we can find it. It's a neat idea, but this gives them something like 1 to 10 megahertz per channel times 100,000 channels all the time. So there's a lot of computing effort in them, but we have already a prototype running. So not with 100,000 channels, but with quite a few, let's say 100 or so. They do it in the existing high power computing facility. It's very strange because they just fire the data away and it's basically lost in the data nirvana. And then they have to search it again with algorithms. So it's quite interesting. So it's very new technology. And yeah, it's not my field, obviously, but it's interesting.
Maybe I can have also a comment here. Thank you very much for different type of detectors or sensors, as you just mentioned. There, of course, among the many different types of particle detectors that we have, they are working either in the DC range, or they are working on some of them. They may have pulses. Some of them may be counters. Some of them may be, as Jens just mentioned, counting scintillators or whatever. But some of the detectors, they are inherently RF detectors. So that means they are particle counters, as you just mentioned. They are particle detectors whose primary output is an RF signal. And these ones are specifically very interesting, as Jens just showed, for the storage rings of all kinds. You see every one of those rings that you see here is specifically interesting for this case, because what you are interested in is to see either the position. You can imagine it's like a donut. So it's like a huge pipe, donut-like pipe, where the particle beam is traveling inside. And what you want to do is that you want to know exactly what the position of this beam, this needle of the beam is with respect to left and right and up and bottom, because this is a very important information in order to correct the magnetic lattice and do all sort of connections. Or if you want to do it, use it for the tumor therapy, and the location of the beam has to be known. Or you just want to measure the frequency, revolution frequency, or you want to have the beam intensity. So there's a huge amount of different information that you can get from these RF detectors, because these RF detectors are non-destructive. That means they are really just kind of antennas around it. You can be I really hate the name antennas, because they are not really antennas. You can consider them as a secondary loop of a transformer whose primary loop is the particle beam itself. So this is a type of detector that also comes into. Maybe I'm going to talk about that in my flash talk on Thursday. And this is something which we're using, because this continuously gives us a signal from the beam. And suddenly, if there is a change in the beam, be it in a nuclear physics side or the atomic physics side, or just because of bumping into some rest gas molecule, we immediately see that in the frequency spectra. And this is where basically finally GNU Radio comes in, because we need a kind of a very versatile data processing, online data processing and offline data processing. So while we are recording everything to the disk and sending them over to the great green cube over there for data processing, at the same time we have an online eye, just by putting a the graph over there, just take a branch and start to make a Fourier transform and make for example, conditional signal on it. So GR is going to help us. It is, but it's even more going to be included in our workflow in order to make this kind of measurements possible directly from these RF sensors. Thank you.
Yeah, I wish I would get like $1,000 for every time I've been asked, like, why GNU, why radio? Actually, interestingly, when we talked also to digital comm guys, maybe we do less of digital modulation of our particle beams, but they work. I mean, like, I played once Beethoven Fifth on the LAC. That also works as a transmitter. But what I find personally very fascinating is if you look at radio astronomy, for example, you look at pulsars and you get radio waves from the universe that tell you like how stars are being created. How do nebula works? How do stars explode? How do black holes merge? They emit radio waves, and we detect it here with antennas. But these are very rare effects, so you can't conclude much about physics of nature. What we're doing in our lab is basically we build our own stars and our own microscopic black holes, if we could, we wished, but not right energy range, and we just invert the whole problem. So while it's a bit like introverted people, extroverted people. Some look outside, we look inside and trying to recreate on a small scale. But the technology that we use and also the principles are the same. Some people call it synthetic aperture radar. We call it tomography. There are lots of many analogies where, yes, how the signal is generated in the first place is slightly different, but they all turn out to be electromagnetic waves, which are captured by either narrowband or broadband RF signals. And very exciting, very exciting. So you're all experts now in accelerators. Very good.
So I actually got two questions related to synchronization again, which is more my field. Small question first. You mentioned that the source of ions is 50 Hertz synchronized to the GPS to the grid. But that's
the complete accelerator actually. We are able to change the complete setup of this linear accelerator, 130 meter, including the sources, 50 times per second. So basically, it's like you have to imagine it's like maybe like a freight train with all empty wagons. And then the sources have to inject beams. So you can have actually of this 50
but that's not
50 ping series you can have.
I get that, but that's not the actual grid phase, because
it is the actual grid phase.
Because to my knowledge, even though when I was young, the power grid was synchronized to atomic clocks. Nowadays, it's not true anymore.
We actually wait for the grid. It's actually the 50 hertz of the grid is this 50 changes of state of our linear accelerator.
Okay.
And it's not the RF. The RF is 36 and 108 megahertz, but this cycle that you get one bunch of or it's a few bunches, but one we call it bunch train. It's 50 times per second, and it's really synchronized to the grid.
The second question is, in the photonics community, they're used to, and there's still a bit of hype about using femtosecond lasers to synchronize accelerators. In particular, I believe that at DAISY, they actually tried and maybe are still doing that. So why is it they do at DAISY, which makes that necessary or useful, which you don't do or wouldn't want to have that kind of facility for you?
I assume the easiest answer is because this is probably used in a light source. There are a lot of synchrotron light source, something what we don't do, and even now XFEL, so you have free electron lasers, and they are much, much more precise. So we want to somehow stabilize our beam in the order of a millimeter, and they're talking about micrometers. And they, of course, have this very short electron bunches. Our bunches are 300 nanoseconds long. They are just much, much shorter. And if you, of course, want to synchronize something like that, you need an even more exact timing signal. And then on the other hand, of course, we use not only cable-bound, but laser-bound transmission between our lasers, but not in femtoseconds. I mean, this is mostly comes out of laser physics. There's even a big field in accelerator physics now. They actually use a high-power laser to accelerate particles, electrons or protons. And then you get very, very short pulses. And again, if you have a very, very short pulse and you want to do something with it, you need this exact timing. So we don't need it yet.
Maybe I can add to that. The second question is maybe Udo, where are you? Because he's our high petawatt laser expert. He can tell you about the laser. I can tell you at least why we have 50 hertz mains synchronization. It's annoying. If you come from another engineering point of view, so like, why can't you make it exactly 50 hertz? The thing is, a lot of the facility is pulsed, and we're drawing tens of megawatts of power. So if you draw power, and you don't do this with the mains frequency, you get a humongous reactive load. If you have a small load, you would build an AC-DC transformer, have some capacity storage, and then have a DC-DC chopper to get to a nice frequency standard. When this facility was built, this type of storage with capacitor was not possible. So you had to have like flying wheels, which are by themselves are very complicated, very expensive, and also very, very dangerous. Also capacitor banks to buffer 100 megawatt of power. If you built this, CERN did this, they ditched the flying wheel and now have this capacitor banks to have a precise frequency standard, but they basically built 2 shipping containers of bomb, basically. So because when the capacitor flies, you store 100 megawatts over a second or so. There's so much stored energy and that's the reasons why for power efficiency and simplicity, people use 50 hertz mains, which is annoying. But what we do is once it comes to the SIS-18, we say like, let's wait like just one phase and say like when the time is right. And we measure this with White Rabbit. This is the zero crossing of the mains frequency in White Rabbit. And then say like, now it's an opportune moment to inject. And then we can buffer this uncertainty of 20 milliseconds. We can buffer it then while storing the particles injection. There's also David Ondrejka, who has been pioneering the synchronization between UNILAC and SIS-18. But this is a major challenge, or let's say major interesting problem we were working on.